It is a prominent scientist, Walter Kohn, who is the designer of modern density functional theory and so on. And main contribution that we didn't start it, we will probably cover it next week, is conversion of the principles of density functional theory, which we are already more or less acquainted with, into the flow chart that looks in a very similar way as a flow chart for the Hartree-Fock theory. So so-called self-consistent procedure. So original density functional theory was based on theorems, and it was focused only on concept of density. So there were no orbitals as in Hartree-Fock theory. And we are going to spend maybe a couple of slides on the second Kohn theorem, but later on we will go into the productive, practical implementation of these theories, and from orbital free we will go to Kohn-Sham theory, which is DFT with orbitals. Molecular orbitals, or as sometimes people say Kohn-Sham orbitals. In this course, we are not covering orbital free DFT, and in your previous homework, you were already illustrating, you were plotting the orbitals, which means we are following Kohn-Sham procedure, so it is more narrow than a genuine DFT. And orbital free DFT is used by people who trying to model, for example, nuclear explosion or very high pressure. So in regular conditions, for chemistry, DFT with orbitals is really great discovery. So theorems. Here is the theorem number one that you are aware of. So knowledge of density, and here we do not state that it is some specific density, just any density for a given molecule defines in non-ambiguous way potential, external potential, which means where ions are located and how they attract electrons, wave function, ground state wave function of this multi-electron system, and molecular Hamiltonian. And in order to memorize this theorem, we were looking on the fingerprints of criminals last time, right? You remember it, do you? I see.
Yep.
Yep. Kia, I see question in your eyes. Do you remember fingerprints and bad men? Okay. So now we will skim through the second theorem. So suppose we do know the density, absolutely correct density for the ground state. So if we know this ground state density, it determines minimal, absolutely correct total energy of the system. And if we modify the density, if we perturb it in comparison to the ground state density, then the energy will become bigger than the ground state. So please let me know if no, I have a better idea. Let me ask you one by one to formulate this theorem as you your impression about this theorem. So, Kea, I just thank you for having your camera on. Therefore, I see you first. Would you please share your impression about this second theorem, how you interpret it? Do not worry, just your first impressions. And your microphone, I do not hear.
Okay.
Just help me to formulate. Like you can tell something very basic. What this theorem is about? What are the actors in this theater play? Which symbols you see?
It's showing the energy of the. Then actually, it's a E means energy and rho is the density. So it's shows for 0. That means it's shows the density of the ground state density.
Yeah.
Ground state density, and that one that one also energy. It's shows the energy of the like in a ground state energy, which is smaller than partial total energy. No, it's not total energy. It's a trial. You wrote in there is trial energy.
Okay. Yep. Very good. I even do not know if I need to ask anyone else. Lola, would you like to share your vision? What you see, or if you do not like something about the theorem, just tell what is wrong with it or what you do not like. Just share your impression and thoughts, please.
So I was going to ask a question right before you ask your question, but
okay, yeah, go ahead.
Okay, so what I got from what you said is that when the density of state is
no, wait, stop. Density of state and density of electrons are different things.
Oh, sorry, yeah.
Please keep going. So it is not density of state. It is DOS. Okay. It is for density of states. It depends on energy, right? And here we are talking about density of electrons, which is a function of position. So density of electrons, which is a function of position in space. Okay. Yeah. Please continue.
Okay. So what I got from what you said is when, according to this theorem, when the density of electron is perturbed, it will take the form of this density trial, but that the energy of this perturbed density will be greater than the energy of the ground state.
Perfect.
My question
is absolutely correct. And you save the rest of the class from speaking. Yes, I just do not know what to add. Many things. It's really really good.
Sir, it's yes. So you just asked me question suddenly. So it's like the electron density is function, electron density function that actually used to minimize the energy of the overall function.
Mm-hmm.
When we want to like define the true electron density, so we want to use that one. Is and
so
maybe
this density is it is density of all electrons.
Density of all electrons.
So density of all electrons. Okay. Are there more?
And
Please ask more questions. And I really would like to involve everyone into discussion, but I just do not know how to improve because Kia and Lola covered everything.
no, the right side, that one should be the um, E row total, right? Or
It is both on the left and right. It is row total,
mhm,
but the one here, row not row zero,
mhm.
is density that corresponds to ground state
Okay,
to optimize to ideal correct ground state. And trial, it means some arbitrary density.
okay, orbit. Okay,
Here is letter A, not orbital, but arbitrary,
RBC.
which means like random.
Mhm. Now it's good.
Okay. Maybe let's keep discussing. Sarah, would you like to share your formulation? How do you interpret this statement?
Um, from previous session, I think said that if we know the density of electrons, and then we can determine the external potential and the total energy.
Mm-hmm.
Yeah.
Well, last I believe in the theorem that we discussed on last meeting is not telling about energy so explicitly. It uses energy. We found we came from contraries. So A plus B is smaller than B plus A. So we were operating the concept of energy, but the formulation of theorem is not talking about it. It tells just that density determines everything, including energy, just determines. And the second theorem tells that if the density is corresponds to ground state, then the energy will be minimum. So this symbol less means that this energy is absolute minimum.
Mm-hmm. Yes.
Make sense?
Yeah.
So absolute minimum. Okay. Yeah. Thank you, Sarah. Lina, would you like to share your impressions about this statement?
Where is Lina? I don't know Lina is here or not. Lina is not here, I guess.
Oh, she's not here. I remember she was connecting. Maybe she disconnect, or maybe she needs to let her in, and I missed it. Oh, okay.
She was there. She was there. Maybe some problem with the internet. I don't know.
Okay. Yeah, 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 yeah. Okay, we'll continue anyway. So, Stephen, would you like to share your vision of the second quant theorem, if you like to? Oh, maybe the microphone is not working. Okay, Boston, uh, would you be interested to share your?
Yeah, so I'm not sure I can add anything else that hasn't been said, but my thoughts of it, my ideas of it is that you can try and arrive at the correct density by by inputting trial densities and finding the minimum energy output that gives, and that should correspond to the minimum density.
Okay.
And so that's what I'm getting from it.
Okay, yeah, I like it. I like it, and you are already setting up.
And then knowing that should tell you a lot of other things about the property. So
exactly. From your formulation, I see that you are already targeting the practical approach. So you are looking how to find this ground state density, which is actually a task of the theory. So the theorem just tells that one can find, if one knows this minimal ground state density, then one will find minimal energy. And you are thinking broader, like how to find this ground state density. Good, very good. So let's go over the proof. And I hate it because it is either too simple or too complicated. I'm not getting why one calls it a theorem. When one looks on the proof, it looks too natural. Okay, so we need to, and improve. If you plan to watch, or you were watching recordings from previous years, I spent the whole lecture and like maybe one slide per each line of this proof, but it seems we can do it in one slide. So we need to arrive to this last line. We start from the declaration that energy depends on the density as a function. And then we need to chop the total energy on three categories in the same way as we do for Hamiltonian. So kinetic energy contribution, the interaction with nuclei, and interaction between electrons. The density is defined in a such way that integral of density will give number of electrons. The density is always positive. And if we do know our absolute minimum density and trial density, we can convert each of them into wave functions. So from minimal ground state density, we can find ground state wave function, and from trial density, we can find trial wave function. So this possibility to convert density into wave function follows from the first theorem. So since density determines everything, it also theorem. It also determines wave function, right? Yes or no? Now we are going to practice variational principle or variational theorem. Variational. So which refers to wave functions and Hamiltonians. So in order to practice variational principle, we are constructing the Hamiltonian, which is sandwiched between wave function in a standard way as we do expectation values in quantum theory. And we can do it twice. I'll read it later. There is a quite long writing in the chat line. So we are comparing total energy. We are practicing variational theorem 2 times. Once with ground state wave function, which is obtained from density, and another time we practice it from the trial wave function, which is obtained from trial density. Yes or no?
Yes.
Okay, so I didn't violate any logic in this step. Just blindly follow applying variational principle to these 2 wave functions. And now, what does variational theorem tell us? That if we have trial wave function which is ground state wave function plus some perturbation, then the energy of the corresponding to perturbed trial wave function will be bigger than energy corresponding to ground state wave function. So basically, we just map variational theorem onto the language of densities. So based on variational theorem, the energy for ground state density and ground will be smaller than energy of the trial density. And in order to arrive to this conclusion, we used first step. We converted density into wave function from the first theorem. And second, we practiced variational theorem. By combining these 2 things, we see that if density for the ground state is known, then it will provide absolute minimum of energy. Any objection? So let me. There was a quite long so I think, okay, you have taken the formulation of the theorem from open sources. Please copy paste it to everyone. So it's a good thing, and maybe it will bring additional inspiration to everyone. Okay, yeah, thank you. So I see that either everyone is very happy with theorem or everyone is very irritated. Is it so? Let's complete this story about theorems and go more to the practical aspects. So based on these theorems, one can go into attempt to solve practical problems in the following way. One needs to find the ground state density in order to find all observables. So in narrow sense,
Professor,
yes.
So in the first equation you wrote that rho r arrow, that sign, the above one, that means that potential is external potential energy. See, you wrote ext, that means you are just considering external potential energy.
Yes. So so here is the logic, at least as I understand it. Density defines everything, including external potential. So there is no doubt that density determines kinetic energy and electron-electron interaction. But it is most surprising that it also determines external potential.
So you just consider external potential energy. So you don't want to consider internal potential energy.
So I see your question. So the energy is, I will go to the previous slide, is composed of kinetic, electron interaction, and nuclear.
Yes.
So the nuclear part is corresponds to external potential. So it is notation. The kinetic energy and electron interaction energy are considered internal.
Okay.
Okay. Does it clarify your question?
Yeah.
Okay. Yeah. Thank you. So right now, our goal for the next week and for remaining minutes of today will be to design a procedure that will find rho naught of R. Because theorems only tell that if it is known, then the energy will be minimal. And if one also knows these rectangular brackets, the functional. But the theorems do not tell anything how where this function or how to fabricate this function. And the theorem doesn't.
Professor, I have a message from Lena. Actually, her laptop is not working. That's why it's frozen. She said.
Okay.
Lena's laptop.
Yeah. Thank you for passing it on.
I get disconnected. Oh my god.
Welcome back. You just missed boring proof of a theorem, and you didn't miss any practically important things. So
I was connected from
the rest of the class is
from the campus. But today
that's okay. Rest of the class is accumulating irritation against instructor for this boring theorem, and you are the only person who missed it, and you're like, oh, let's do fun stuff and practical things. Okay, so we need a procedure that will help us to find the density for the ground state. And all our efforts in remaining minutes today and next week will be oriented to this goal. The theorems that Lena successfully missed are just telling if this density is known, then the energy is known. But how to find energy out of density is not clear. There is no theorems do not tell how to find it, and the theorems also do not tell how to find actual ground state density. So in your homework, you are already doing these things, but right by now we do not know how it is done. And just as a little hint, the procedure is similar to Hartree-Fock self-consistent procedure, but we need to go over it. Okay. So on this way, we are going to establish, so maybe in a week from now, the self-consistent loop, how one goes from density to external potential, to orbitals, to total energy, to and then back to density. And by cycling this procedure, we will get more and more precise total energy. So it's basically similar to Hartree-Fock. But in order to practice it, we need to consider several concepts. So we need to concept of functional derivative. We need to introduce an auxiliary universe where electrons do not interact with each other, and we need to pave a way from our real universe to this auxiliary universe where they do not interact and return back. And then after this auxiliary universe, we need to discuss a practical way how to construct density out of orbitals. So from homeworks, you are already successful in plotting orbitals, but now we need to discuss procedure, how these orbitals help to construct total density. And with all these procedures, we will be able to arrive to our main goal for this self-consistent iterative stuff. So before we go in, either before we go into details or before we complete our meeting for today, I want to bring a rational motivation why one needs orbitals. So based on the theorems, density functional C or E must work without any orbitals. One needs only density and some function that converts density into energy. But practically, there is a challenge in converting density into kinetic energy. It's not like undoable, but it is not efficient to compute kinetic energy out of total density, on one hand. On another hand, through our experience in Hartree-Fock theory and through basic concepts of quantum theory, there is a really comfortable procedure of extracting kinetic energy, the first part of the function, out of orbitals. So if we know orbitals, we can practice second derivative over space, the kinetic energy operator, and easily, in a very traditional way, to find kinetic energy. So the motivation, the reason to use orbitals is not because they look nice and chemists like molecular orbitals, but because computation of kinetic energy is very efficient in terms of orbitals. Okay, so and now let's see what else we today. Okay, so here are some key notations that one needs for the actual density functional theory as it is published and as one is describing it in the methods section if you ever will write papers on density functional theory, and hopefully if you will write your reports by the end of semester. So in addition to your results, you will need to explain methods. And in methods, one needs to explain how DFT works in a brief way, like a paragraph or two. So while looking on these equations for the first time, I can be either scared or irritated. It's very normal. So I was after like getting degrees and started practicing some research, I was not doing computational chemistry for first several years, and I was seeing equations like this on the on scientific presentations, and was either scared or irritated. So if you have this feeling, it's quite normal. But I need to let my assistant out of the room. Just a second. So, what can we tell about this equation? So um, it deals with energy of electrons interacting with nuclei, right? And by some reason, it doesn't use wave function. Like if we get training in basic of quantum theory, any energy is expressed as a matrix element of wave function operator, like Hamiltonian of something or any other operator, and wave function, right? And here, by some reason, I do not see wave function, but I see a density instead. Yeah, that's fine, and I'm about to finish. So the V, which is external potential that Kia was asking about, is interaction between ions and electrons. And the density is can be considered in terms of wave function with star times wave function without star. So this first equation originates from standard way to find energy. But instead of using wave function, we use density. Now, here are few tricks that are very simple and basic, but and you will learn it in 3 minutes, and for me it took 3 years. So basic calculus. If one, let me write it aside. And I understand you need to go to other class, and I'll finish really quick. It's not much. So if you have derivative and you have a function, then it can be expressed as derivative times derivative of independent variable. So here I want to bring up new view on this product. So the meaning of density times element of volume means can be interpreted as increment of density. Increment of density. And now our integration will include integration not over the elements of volume, not over the space, but over the density in some crazy, it's not Cartesian space, it's just some abstract space of density, right? So our independent variable becomes density. And if you remove an integral and look just for infinitesimal contribution to energy from infinitesimal contribution of density, then it will be potential times increment of density. So please say yes or no here. Is it more or less okay?
Just repeat the sentence, Professor.
Okay. So I'm going from first line to the third line, and I'm looking for contribution to electron to nuclear interaction from a little contribution to density. Like if density is incremented in one area of space or everywhere, if density is increased, how much the energy will increase. And in order to find it, we multiply increment in density times the potential. And it goes through the line number 2.
Yeah.
Okay?
Yeah, now it makes sense.
Okay. And now there is one basic step which may throw just mind will boil. Let's divide left and right side of this equation by increment of density. Is it okay? I just take line number 3 and divide.
It's okay.
Okay, divide left and right by this delta rho. Now, you didn't protest, you didn't scream, stop, I do not believe it. But it is really like very key step in the knowledge of the whole human civilization. So we do have ratio of increment of energy to increment of density. And density is not a number, is a function. So we even can have the limit for this delta rho goes to 0. And then this will be a definition of functional derivative. So it is functional derivative. Not function, but functional derivative. No derivative. So by functional derivative of energy in respect to density, one is getting external potential. So I believe I took over too much time from your precious schedule. I think we need to finish now. But think about this new concept, and the new steps next week will be based on it. So this concept of functional derivative is the heart of the practical side of DFT. Okay, meeting is done. Everyone is welcome to disconnect or depart the room, and my assistant has already departed. So thank you for investing your time, and meeting is done. Any questions are okay. I'll stay here and answer them.